Hello everyone, good afternoon, good morning, or good evening. Today I will be presenting how the test and cert instruction is used in operation system in implement mutual exclusion and how we can demonstrate this behavior in a multi-threaded. First, in the assessment, I implement a test and send function that read the current log value and set it to 1. Even though this is a software simulation, it uh, closely mirrors the really hardware instruction. And the second one is test 1B. We create a program with 5 threads, each thread with five threads. Each thread have 4 things can do. First, try to acquire the log using test and cert. Second, print its thread ID inside the critical section. Third, the next is sleeping for a short random time. The last one is releases the log. And when the program runs, the output shows that only one thread enters the critical section at a time. Then I will explain why test and cert ensures mutual exclusion. Because test and ensures mutual exclusion because the entire operation is atomic. Only one thread can ever observe the log as free, while all others must wait. And the next question is why base waiting is inefficient for inefficient. Base waiting is inefficient for several reasons. It will waste CPU cycle because threads keep check the log, and it increase power composition and the CPU temperature. On the single core CPU, spinning threads may prevent the lockout thread from running. High contention leads to significant performance loss. Thank you. This is the first question.
Hello everyone, my name is Chen Zhiyang, and for the assignment 2, I worked for question 2. So I'm implementing accounting C4 with FIFO fairness. So accounting stamp file manages assign to multiple identical resources. In our case, three available slots, unlike a binary semaphore that only allows one thread at a time. This allows controlled concurrently improving throughout code. And then my implementation, the semaphore class has a value each initialized to 3, a FIFO hole to hold waiting threads, waiting and signal methods, and in wait. If a slot is free, the thread proceeds. If not, it's added to the queue and blocked. No busy waiting. The longest waiting thread is woken from the queue, ensuring FIFO fairness. So there are 5 threads. And demonstration. I have created 5 threads competing for the 3 slots. The output clearly shows, and only 3 threads enter the critical sections at once. And then the remaining threads waiting in order and enter one by one as slots free. And then when its design works, we can compare the counting and the binary. We need to allow 3 concurrently threads, not just one. And FIFO prevents starvation. Threads are served in question and order. No, now, so now wait forever. And mutual exclusion and fairness. An internal lock protects the semi-fair state, and the FIFO queen ensures fair weak ops. And this is an efficient, fair synchronization tool suitable for resource pools like data bus and connections of multiple slot buffers. That's all. My thank you.
Starting at height position 53, first FCFS, it strictly follows the arrival order. It is professions fair, but look at this efficiency zigzag movement. It has the slowest performance. Next, SSTF. It greatly picks the closest request, moving 53 to 65. It gives the best throughput. It kills starvation if new jobs arrive near 53. This far request at 183 will never get served. To fix starvation, we use scan, the elevator algorithm. It sweeps to the end and back. It guarantees serves for everyone. However, it's beside tracks in the model get served twice as often as the edges. Finally, C-scan, it jumps back to the start without serving. Why? To provide a uniform wait time. It treats the edges exactly the same as the middle, making it perfect for systems needing consistent response times. In summary, use SSTF for speed, but use C-scan for fairness and heavy load. Thanks.